Okay, I believe we are streaming. So we've got a first version of SPIRiT implemented, and it accommodates, when epsilon equals 0 and when epsilon not's equal to 0. Hard data consistency and maybe what we'll call soft data consistency. Just checking the stream here. Okay. Today, what we're going to try and do is implement a first version of SPIRiT regularization. And since we've already got the kinks worked out in SPIRiT in one code, it really shouldn't take that long. I'm not saying it's not going to take that long, but it shouldn't. So away we go. All right. I notice that when I'm watching my own streams, my sentences get broken up when I'm trying to both code and speak at the same time. So I'm going to try and consciously make an effort to either code or speak. Hopefully that makes it clear what we're trying to do. Okay, so here I'm going to write down the problem that we're trying to solve. We're going to minimize So this is interesting. So what do all these things mean? X is the optimization variable. It represents the image that we're going to try to reconstruct. By solving this problem, we will reconstruct an image. S are the sensitivity maps. F represents a block matrix of discrete Fourier transforms. And D isolates just the data that was collected. So this says that if I take the image X, this says that if I take the image X, multiply by the sensitivity maps, take the Fourier transform, and then just look at the data values that were collected, look at the frequencies that were collected, those values should match the data that was collected by the machine well. Okay? That's what this first term says. And so we sometimes call this term the data consistency term, whatever. Lambda is a regularization variable. So this is the regularization function. If lambda is 0, then we're not using regularization at all. If the higher we turn up lambda, the more we make this important. The more we say, we really want to satisfy this. Okay. And so this says, if we take the SPIRiT kernel and apply it to the k-space locations, then and subtract away those k-space locations, then that should be small, right? That's the assumption of SPIRiT. Okay. How do we get these k-space locations? We take FSX. Right? K is equal to FSX. If we take the image, multiply by the sensitivity maps, and then take the Fourier transform of each sensitivity image, sensitized image, we get the k-space locations for all the coils. One thing I hadn't realized before, but it is obvious now, this is a least squares problem. Though it's a little hidden. Minimize. So I'll put lambda over 2 here. Same thing, so that when we take the derivative and drop down this 2, though if we're gonna use LSQR, then we don't really have to do that. We'll start like this. So this is equivalent to minimizing. This is going to be hard to put into D, F, S on the top. W minus I, F, S on bottom. So this is a block matrix now. That's the equivalent least squares problem. You know, obviously I could do this, right? Because minimizing the square of a norm is the same thing as minimizing a norm. So taking that away, this is a least squares problem. These two things are equivalent. Okay, great. So now we're going to call LSQR on this. I think we already have much of this code written. Let's see. Here we're going to take X naught. Now what's X naught? X naught is the original image, and we'll just set it to zeros. It's the original guess of our image. Like I said, we'll set it to zeros. Okay. Now all we need to create is apply A and B. Ooh. Let's call this Y. Let's call this Y. Apply A and B. B is going to be this block matrix here, Y0. This block column vector, Y0. You know, we can do that right now. We're going to need a sample mask. I never did find out, do I actually need the equals 1 here or not? Looks like we do. That's unfortunate. Did I just make the same mistake that we made before? Okay, so now I'm questioning. What is the output of that? What's its size? It's the size of K data. Okay. I'll bet you that works. We need to apply W. Where's that? And we're going to need W for apply W. Let's put all that in. So here we've got apply W. I'm going to create apply, well, I don't know. I'm going to create apply W minus I. Does that work if you only pass in one argument? Guess we're going to find out. Okay, so now I've got this, right? I'm going to call this top one A1 and this bottom one A2. Okay, or maybe I'll call it A top, A bottom. That's better. Okay, so A top. Top A. Well, A top. What is A top? We multiply by the sensitivity masks. Then take the Fourier transform. And then just look at the values, the frequencies that were collected. Just return the values at the frequencies that were collected. I think we went through this thing where LSQR assumes that everything's a vector, the inputs and the outputs are vector. So in here is going to be a vector. We're going to do reshape. We'll do the reshaping for apply A and for nothing else. Okay, now we need the adjoint of this operation. So I don't have to continuously allocate and deallocate array. I'm going to pre-allocate a matrix of size equal to k data. I'll call it zero filled. ZF is equal to zeros size k data. We actually know the size of k data. I don't know that it's any faster to use that, but whatever. Now, one thing to note is that we don't yet have the sensitivity maps. I'll show you how to get that in a second. Okay, so now I'm going to take ZF, wherever sample mask is equal to 1, and send in the input. That's the adjoint of this line. Now we need to take the adjoint of this line. The adjoint of FFT2 is not IFFT2. Some might think it is. And if FFT2 were the unitary version of the FFT, then it would be. But in this case, it's not. And I think in dwarklib we have yeah. Oh, yeah, okay. FFT2H, exactly. Okay. And remember, when you're taking the adjoint, like if you take A B transpose, that's equal to B transpose A transpose. So the adjoints happen in the reverse order, which is why I took this output line and did this first. So what is the adjoint? So now we could just take the adjoint of this FFT2. Now I just need the adjoint of this. So this operation, if we were to write it out in matrix form, would be S1 transpose, oh no, S1, yeah, I guess, well, S1, S2, S3, up to the number of coils. Times n. That's what that is. And here, so this is a block column matrix. That means its adjoint is S1, S2, S3, SC. That's the adjoint operation. So out is equal to conjugate. And then we're going to turn out into a column vector, because that's what LSQR assumes we're using. That might be a top. Now we need a bottom. Again, I forgot. We're going to do this vectorization and devectorization in the function apply A. This should be no transp. Already created a terrible bug. Luckily we caught it. I'm sure there are others. So what's a bottom going to be? Well, it's just going to be this. And so this brings up an interesting thing. We're doing this in a top, and we're going to have to do that same thing in a bottom. So instead of replicating that operation, which is actually quite expensive, we're just going to create an apply A, and we're going to create, we're going to put this operation here. These are the Fourier values, so we'll call this FLs. The only thing that isn't in a top, that's in a top outside of this, is just this sample mask operation. So this is saying the adjoint of A times in. This is going to be F times the adjoint of H times in, F being the Fourier transform. And here I forgot to do the sum operation, so the sum is going to be in the third dimension. Okay, great. Here we got a top. This is going to be out top. This is incorrect. We're going to have to put something here. This is a top adjoint in. We're going to need a bottom adjoint in. If A is equal to A1, A2, then the adjoint of A is equal to A1 adjoint A2 adjoint. That is, this is a column block matrix and this is a row block matrix. So when we multiply this times something like x1, x2, then we're going to take a1h times x1 plus a2h times x2. That plus is a summation. That's the summation that I just implemented. Where was it? The sum that I just told you I forgot about? Here. And also, we're going to add these things together now. I think they're both going to be the same size, and I think they're going to be the same size of the image. So what I'm going to do is put an error statement here with a check, with a reminder to check that a top h in and a bottom h in are the same size. If they're not, we'll deal with it. We need out bottom, a bottom vals out is going to equal. Now here, these are not the same size at all. So I'm going to take this, put it here, take this, out top, out bottom. This is concatenating the results of these two operations here. These error notifications that MATLAB is giving me are because this error is preventing either of these from variables from ever being used. It will never hit this line. That's fine. I know that. This is just a check. Oh my goodness. I just deleted a bunch of stuff. I just closed a bunch of stuff. Where is this? Okay, well, let's see. Hopefully I didn't save anything that I just changed. Oh my gosh, rekin. More than one bug already. I guess we're outputting image here, not out. Just fine. Now you might notice we don't yet have a bottom implemented, so let's do that. Okay, so what is a bottom? We're going to take, these Fourier values, fsx, we're going to multiply it by apply w minus I. That is a bottom. Interesting. So we don't really need, a bottom anymore. I think it makes the code cleaner to call this a bottom. And this is, I think that's fine. Did we do it? No, we didn't. Why not? Because we haven't yet done this vectorization and devectorization thing. So this is certainly outputting vectors. But this needs, so here's part of the problem. This needs to be in one and in two, or maybe in top or in bottom. That might be easier. So we need those variables. And then in here is a vector, but this is taking FFT2, so we need to reshape in to the size that the FFT2 requires, or that this multiplication by SMAP requires. What size is that? It's the size of the image. I don't think we yet have the size of the image. Oh, we do? Nice. Okay. The output of A top is something the size of K data, and the output of the bottom is also something the size of K data. That makes it easy. There you go. All right, that's a problem because this thinks it isn't being used. Oh, no, I was wrong. This does not output something the size of K data. The output of this is the output of D, and the output of D is the number of samples. Where does sample mass get made? It doesn't get made? Oh, you're going to need that. Use NNZ. Okay, number non-zero. That's fine. I will happily do that. Coming back here, instead of NK data, we go from NK data from 1 to N samples, and then in bottom is going to be all the values in the vector beyond the number of samples. It looks like we no longer need NK data, so that's nice. We're still not using this. Why not? Tough, 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 tough. All right, the inefficient way to do this is like this, and maybe that's where we leave it for now. It's just a shame, though. It looks like I can't think of a way with MATLAB to avoid this, to avoid a memory allocation. I could do this. But then I have to do this. And this is a memory allocation and a copy. So why do that? I can't think of a way to avoid that memory allocation. Okay. Let's see where it breaks. Okay, it's a simple fix. I think this is pre-compiled, but I clearly don't want to do that right now. What is a MATLAB ASV file? Autosave files can save you time. By default, the backup file is stored in the same location with the same name as the original file, but has an extension for ASV. Okay. Is it just a backup file, or is it actually like a pre-compiled thing? Autosave, so it's not pre-compiled. It really is just meant to be a backup system. Okay. I guess I don't need to worry about that. I don't have usage. Let's add usage to the original MRI Recon SPIRiT. Does it actually say it? Look at that. That is code we could check in right now. Oh, I guess I need... dips. Dips. Disp for display. Okay, so I think that's why I do this thing. If nr out is greater than 0, I don't like having this show up, and I think the nrgout thing lets me prevent it unless we do something like this. And it tells you what it was. And then if we do that, great, it all works. Okay. You know, nothing says we can't add usage before we get the thing useful. Although, we're going to add parameters later, so we're not going to do that now. All right, so I think we fixed one bug. Now we got another. And coils, of course. SMAPs. Never told you how to find the SMAPs. Okay, org lib sensitivity. I've got a function called make sensitivity maps. Now, I've got one called make and find. Now, this find sensitivity maps, probably should be called make sensitivity maps, but this is for MR spectroscopy, which is not what we're doing here. Compute best sensitivity built so far is basically wrong. I mean, it does what it was supposed to do, but I don't think this is useful. So we won't even worry about that. Here we have a way to make sensitivity maps, and it gives you several different options for making them. These are old ways. So this is the method of Prusman. This is a very, very simple algorithm where I think you just take the images of the reconstructed, well, the zero field reconstructed image and divide by, it doesn't matter. I think the whole point is that this makes a sensitivity map with the way that's reasonable, but maybe not the best. The best way to make sensitivity maps, people claim, is SPIRiT. But SPIRiT doesn't make a sensitivity map. SPIRiT makes a set of sensitivity maps, and I haven't yet figured out how to create a single sensitivity map from that set of sensitivity maps. So this is what I'm using so far. Now, it's very common for people to have their own ways to create sensitivity maps or to already have them created. So we're going to let people pass in sensitivity maps. Optionally pass them in. And so we're only going to create them if people haven't passed them in. Seems to be running. I forgot to tell the people that I've been streaming. What will my audience do? User supplied function failed. Okay. So we got as far as calculating LSQR. I don't know. Oh, right. That's all to load stuff in. Undefined function temp for arguments of type logical. What? So first, let's see how long it takes to make these sensitivity maps. Okay, it takes a while. So we're going to save these sensitivity maps as their own map file and load them in while we're trying to debug this thing. And of course, we're going to put the load statement in the first column so that, like this error statement, we'll be reminded that we have to delete them later. It takes a long while. I think this would take much less time if we had multiple workers set up. I think it's parallelizable, and I think it's parallelized. Okay, so save smaps.map map smaps. I think this is just going to bypass that because the load function makes the number of smaps non-zero. Okay. Here's apply A. Let's see where we get to. A top. Temp does not exist. This should be in. And oh, we did put is numeric there earlier. Okay. Looks like that one broke. Let's see what the problem is with A bottom. What? We've got apply W right here. Why doesn't it go into apply W? This might be because if nrin is less than 2 or string composed op, string compare, no transpose, then we do this, else we do this. I wonder if that was it. Yeah, okay. MN. Doesn't like that. S image, because we don't have M and N, we have S image. think S image is a, here's what I'm going to do. S image 1, S image 2. S image is a row vector, so I could just put S image here. Why not? All right, let's take a look at these sensitivity maps. Yeah, they look somewhat like sensitivity maps. You do see some of the structure of the ankle, which is not good, which is why people use SPIRiT instead. So hopefully that's in our future. We're at the point where we're doing this check. So a top HN is 256 by 256 by 8. A bottom HN is 256 by 256 by 8. They are indeed the same size. One thing, we're going to take advantage of our input parameter. So we're going to take this and put it on the outside. I think we should have an SMAPS variable. Indeed we do. Okay. And so now when we get here, we're passing in an S. Oh, I forgot to pass it in. So now when we get here, it shouldn't call it MRI sensitivity maps here. It doesn't. We know that because it takes a long time and it was nearly instantaneous. And so off we go with the rest of our code. What's the problem? User supplied. Wow, okay. So let's make sure that we got both of these up and running. That works. What? Why didn't that work? Because this does not reshape correctly. What's the issue? We need to resize it to the size of S image. Oh, we don't need the size of S image, we just want S image. Wait, that's not the number of samples. In top is just that. We don't actually have to make that copy, so I'm not going to. Okay, moving on. I'll put an image star. it appears we're at the point where LSQR is running. Where's lambda? I forgot to include lambda. Okay. I forgot to include this lambda in the A matrix. And on top of that, I forgot to actually include lambda. I'm going to make it a parameter because eventually I'm not going to use this. I'm going to do something different, but that's for another day. I like to add parameters alphabetically. Its default value, I'm going to make 0. Now, did I get it right? Is it actually square root of lambda here? If I move this lambda to the inside, let's say I had a scalar t here. I'm taking the norm of t and squaring it. So this is equivalent to saying t squared and removing the t here. So yeah, I think this is square root of lambda. And so for a bottom, I'm going to put square root of lambda times that. Now we got to pass in a lambda. Okay, so now I think I'm accounting for lambda. So lambda was 1 before, now it's 1 times 10 to the negative 3. Doesn't really matter. Let's see what happens. We haven't done checks. We haven't checked that any of our adjoint operations are correct. You don't say. That's undersampling of by 3. Looks like it's working. Okay. We no longer need S maps. Let's check in the dwarklib files first. Right, I had this twice, and this one was actually correct, so I got rid of this. And the default is to use 1, I think. Let's make sure. Oh, shoot. No. Yep, the default algorithm is Prusman's algorithm, so that's good. All right, nothing there. What did we change in MRI recon spirit? Did we add usage? Yep. Uh-oh. Oh, okay, to the wrong one. Okay, so git commit, adding MRI recon spirit. Git add run MRI recon, run git commit, adding MRI recon spirit reg to the repository. Git add MRI recon spirit. Added usage to MRI recon spirit. And that is a good day's work. Okay, so next time we can add the checks to make sure that the adjuvants are going well. That would be a very good thing to do. The other thing that we're going to do is instead of putting this as a regularization function, a regularization term into the objective function, we are instead going to add it as a constraint with a bound. And that will make it, infinitely more usable because no one knows how to choose lambda. It's still reasonable to call it spirit regularization for reasons that we'll discuss next time. With that, that's the end of the stream. Thank you everyone for stopping by.